Welcome to another video. In this video, we move beyond simple linear regression and explore models that include multiple predictors or multiple independent variables. Many real-world regression problems involve more than one independent variable. When a regression model includes two or more predictors, it is called a multiple linear regression model. In this setting, the unknown beta parameters are referred to as regression coefficients. Geometrically, a multiple regression model describes a hyperplane in a k-dimensional predictor space, where k is the number of independent variables. Each coefficient beta j represents the expected change in the response variable y for a one-unit increase in predictor xj, holding all other predictors constant. This holding other variables constant interpretation is a key feature of multiple regression. It is important to understand what makes a model linear. Linearity does not refer to the shape of the relationship between the predictors and the response in the data space. Instead, a regression model is called linear if it is linear in the unknown parameters, the beta coefficients. This means that even if the relationship between x and y appears curved or complex, the model is still considered a linear regression model as long as the beta coefficients enter the model linearly. In other words, linearity refers to the coefficients, not the predictors themselves. This distinction becomes especially important as we move from simple linear regression to multiple regression and more flexible model forms. Let's go over an example together. We are given a company's data that includes the amount of money spent on different types of advertising media, including TV, radio, and newspapers, along with the resulting sales. Our goal is to fit a multiple linear regression model that predicts sales based on the company's investments in these different advertising channels. In this model, sales will be the response variable, and advertising expenditures on TV, radio, and newspapers will serve as the predictor variables. By fitting a multiple regression model, not only we can quantify how each type of advertising contributes to sales while accounting for the presence of the other media types, but also assess whether investments in each advertising channel have a statistically significant impact on sales. Looking at the coefficient column, we can report the fitted multiple regression model. Denoting TV by x1, radio by x2, newspaper by x3, and sales by y, the fitted model is y equals 4.3346 plus 0.0538 times x1 plus 0.1100 times x2 plus 0.0063 times x3. However, looking more closely at the regression output, we notice an important difference among the predictors. The t-test associated with the newspaper coefficient has a relatively large p-value. This indicates that, after accounting for TV and radio advertising, spending on newspaper advertising is not statistically significant. In other words, there is not enough evidence to conclude that newspaper advertising has a meaningful impact on sales when the other advertising channels are included in the model. Now, we need to check the adequacy of our model. This Q-plot suggests that the normality assumption is largely reasonable with a few caveats. Most of the points lie close to a straight line, which indicates that the residuals are approximately normally distributed over the central part of the distribution. There are some noticeable deviations at the lower and upper ends of the plot. In particular, a few points in the lower tail fall below the line, and the upper tail shows slight departures as well. This suggests mild tail deviations, possibly indicating slight skewness or a few outliers. These kinds of small departures at the extremes are very common in real data and are usually not a serious concern, especially when the sample size is moderate to large. There is no strong S-shape or severe curvature, so there is no clear evidence of a major violation of normality. Unlike the normality, this residuals plot indicates that the model assumptions are not fully satisfied, and there are signs that the fitted regression model may be inadequate. Unlike a well-behaved residual plot, this plot shows structure rather than randomness. This suggests that the current regression model may be inadequate. Dropping a variable can help sometimes with the adequacy issues, but it usually does not fix the main issues we see in that residual plot. If the adequacy problem is coming from a predictor that is basically noise and adds instability, or multilinearity that inflates standard errors, then removing an unhelpful variable can make the model simpler and sometimes slightly cleaner. In this case, Dropping newspaper makes sense because it is not statistically significant after controlling for TV and radio, and it simplifies interpretation. But if the residual plot still shows structure, we likely need to improve the model form by adding a nonlinear term, like TV squared or radio squared, or adding an interaction, TV times radio. We can observe that even dropping the newspaper is not helping us to address the adequacy issue. It seems we need to improve the model form by adding an interaction, TV times radio. As an exercise, please try fitting a model with the suggested interaction between TV and radio and report if it addresses the adequacy issues. Let's go over the same example and interpret the available partial Python output to answer the following questions. We are given a company's dataset consisting of 200 observations, which includes the amount of money spent on different types of advertising media, TV, radio, and newspapers, along with the resulting sales. Using the provided output, answer the following questions. Report the fitted multiple linear regression model. State the hypotheses for the intercept, TV, radio, and newspaper coefficients, and determine whether each coefficient is statistically significant at a significance level of 0.05. Construct 95% two-sided confidence intervals for the intercept, TV, radio, and newspaper coefficients using the t-critical value of 0.975 with 196 degrees of freedom equal to 1.972. Based on the results of this analysis, discuss what the next modeling step should be. For question 1, we use the reported coefficient column to write the fitted multiple linear regression model. Denoting TV by x1, radio by x2, newspaper by x3, and sales by y, the fitted model is y equals 4.3346 plus 0.0538 times x1 plus 0.1100 times x2 plus 0.0063 times x3. For question 2, we use the estimated coefficients and their corresponding standard errors to construct the t-test statistics for each coefficient. We can then either apply the rejection region approach, using the given critical t-value, or rely on our estimated p-value to determine whether each coefficient is statistically significant at the specified significance level as reported here. For question 3, we use the estimated coefficients, their standard errors, and the given critical t-value to construct two-sided 95% confidence intervals for each regression coefficient. Finally, for question 4, we observe that among the predictor variables, newspaper advertising is not statistically significant. Based on this result, a reasonable next step is to remove the insignificant variable and refit the regression model using only the significant predictors. In simple linear regression, extrapolation is easy to spot. The predictor value is outside the data range. In multiple linear regression, extrapolation can occur even when every predictor is individually within its observed range. This happens because the model is making predictions in a multidimensional space, and the data only occupy a limited region of that space. Hidden extrapolation is risky because the true relationship may change in unobserved regions, interaction effects may exist but are not modeled, and linear trends learned in one region may not hold elsewhere. As a result, predictions can be highly unreliable, even though they appear safe based on marginal ranges. In multiple linear regression, extrapolation can occur even when all predictors are within their individual ranges, if their combination lies outside the region supported by the data. Thank you for watching. I hope this video was helpful, and I look forward to seeing you in the next one.